Welcome to the lecture number 5 in this lecture series, and today we will speak about the improvement of the Pietsch construction of traces due to Pietsch use. Modification. Construction by Pietsch. This is the paper in the Journal of Mathematical Analysis and Applications in 2015. So, as you might remember, when we spoke about the original Pietsch construction, it was the interplay between the operator ideals and the shift monotone sequence ideals. So let me briefly recall you what are these creatures, and then we will go to the modification of the construction. Maybe we will consider a few examples. So first of all, we need the definition of the ordinary numbers. The nth ordinary number of the bounded sequence is given by this. So it's n of x, and it is defined to be supremum of the absolute value of x over all k greater than or equal to. Example. Well, if we have En, which has 0, 1 in the nth coordinate, then the ordinary number of, let's go with En to avoid confusion. En is, what do we have in the first position? 1 in the second position, and up to the position n, and after that the zeros.
It's just a number, right? It's not a sequence.
Well, yeah, I should be able to like this.
Yeah, correct.
So this is the number, this is the sequence. Well, another fairly simple example that if we have considered that already. I just want to briefly recall you about this stuff to make it easy for today. Then, if x coincides with its decreasing rearrangement, so if it's positive and decreasing, then the ordinary number of x is just x. That's it. And two more definitions. The definition of the shift monotone sequence ideal, or rather of a monotone sequence ideal, and then the shift. A subset, a linear subset. Is called a monotone sequence ideal. If for every for every x from E and y from L infinity, the fact that the ordinary numbers of y are dominated by the ordinary numbers of x for every n. So this implies that y is in E. So this is kind of a counterpart of a symmetric sequence ideals. And one more definition. That a monotone okay, I should probably go one by one suggestion. A monotone sequence ideal is called shift monotone. If E is half S plus, well, it doesn't matter because it's a linear subspace. If E is S plus inverse, clearly that every monotone sequence ideal is S minus invariant, because S minus just removes the first coordinate, and so the ordinary numbers of the S minus of x will be dominated by ordinary numbers of x. But not necessarily that not every monotone sequence ideal is S plus invariant. That's why we need an extra definition. And Albert Pietsch established the bijective correspondence between the operator ideals and the shift monotone sequence ideals. And this correspondence is given like this. Shift monotone sequence ideal, we define a ideal of operators to be the set of all bounded operators such that the singular values of A taken at the dyadic positions, so this sequence belongs to E. That's how we define it. The other way around is that these consist of all bounded sequences such that the operator dx belongs to P, where the operator dx is just the dyadic dilation.
When you say ideal E is shifted in one line, it means E equals to S plus E.
It means that for every x from E,
S plus X.
S plus X is
also in here. So does this imply the left shift in the right?
S minus. You mean S minus?
Yeah.
Every monotone sequence ideal is S minus invariant, because when you take an X, S minus just applying S minus, you lose the information. So the ordinary number cannot be greater than the original ordinary numbers.
So can we say E equals to S plus E? I still say it.
Let me just include it.
Yes, I think so,
Yes, because if we have S plus invariance,
Yeah.
then, well, S minus invariant is automatic.
Mm-hmm.
So if this one is in E, then X is also in E because it's S minus invariant.
Mm-hmm.
Yeah. And yeah, let me recall you what is the operator D. So it's a diagonal operator. And on diagonal there is a sequence x0, x1, x1. And then the nth term repeated in 2 to the power of n times. Several very simple examples. Let's see how these correspondence work. If E is B of H, then the corresponding E, the straight E, consists of all sequences such that dx is in E. So all sequences such that this diagonal operator is bounded. But for every bounded x, we will get that dx is a bounded operator. So this is nothing but element. If E is the set of all compact operators, then what will be the straight E? It will be C0. Because we will get a compact operator when the sequence x tends to 0. Oh, yeah, okay. L1. The usual trace class. So here we have that E equals to the set of all sequences such that, well, still, let's go with this. Such that mu k dx from k from 0 to infinity is finite. So that's the definition of L1 infinity. But what do we have in this sequence? We have that every term, first of all, well, it's positive, we take the absolute values of x, and every xn is repeated 2 to the power of n times. So the counterpart of this will be all bounded x's such that the sum from 0 to infinity 2 to the power of k times the absolute value of xk is 2. So that's the shift monotone sequence ideal corresponding to L1.
So the second example, E is just C0 or it's contained in C0?
No, it's just C0.
Okay.
So if we do not speak about the trivial examples like L infinity and the ideal which consists of a zero operator, zero sequence only, then C0 is the largest shift monotone sequence ideal. If we exclude L infinity, then this one is the largest. And the smallest one is the ideal of finitely separated sequences, which corresponds to finite rank operators. Definition. A series A equals to the infinite sum of AK, where we understand the convergence of this series in the operator normal. So this series is called a dyadic representation of A if I have to say that A is a bounded. If the rank of AK is not greater than 2 to the power of k. What are the possible examples of such representations? So for every operator we can write down the Schmidt representation. So it's kind of diagonalizing the operator. The Schmidt, it's not we have, it's the operator has. A has the Schmidt representation. A can be written as some numbers alpha k, and then we need kind of the diagonal stuff uk vk 0 to infinity, where u and v are orthonormal. Orthonormal sequences. So just the usual representation of an operator, diagonalization of the operator. And then we can take AK to be just these. But with some, it's not exactly to do with K anymore. J, and with some from 2K minus 1 to 2K plus 1 minus 1. So the rank of this operator, the way exactly 2 to the power of K terms. So the rank of AKs are exactly 2 to the power of k, and in the operator norm, the series of this operator converges to. So that's the example of the dyadic representation. So let me use the asterisk here. We're going to use this formula. So another definition is that given a shift monotone sequence ideal. Ideal E. The dyadic representation, this one, with this condition, of course, is said to be E representation. A minus from 0 to minus 1. So in the operator norm, so this is the sequence here. Okay. This is a sequence in N. If this sequence belongs to E, then we call it E representation.
Alex,
Yeah.
so UK tensor VK is actually rank 1 operator?
Say it again?
UK tensor VK is a rank 1 operator? The rank of this operator?
The rank of
UK tensor VK?
yeah. Yeah.
So why can you just take AK equals to alpha K times UK tensor VK?
This one?
Yeah, if you just take AK equal to that, then the rank of AK is always less than 2 to the K.
If I'm going with this one. Yeah.
No, if we just let AK equal to alpha K UK tensor VK, not that instead of that one,
Yeah.
then the rank of AK is always less than 1. And it's always less than 2 to the K.
No. It's I'm probably missing something.
Yeah.
So these are the rank 1 operators,
Yes.
but there are infinitely many of them. So this is kind of a diagonalization of the operator A.
Alpha K is just some numbers, right?
Alpha K is numbers.
Numbers. And the operator is a rank 1.
This one,
Yeah. Yes.
not this one.
No, alpha K times that one is also, yeah,
Yeah, rank 1.
rank 1. So why can you just take AK equals to alpha K UK tensor VK? And then-
You mean, okay. So instead of getting up to 2 to the power of K, we can go with approximation by rank 1 operator. Yeah, it will work as well.
Yeah, because you just needed to
Yeah.
get the rank of AK
Yeah.
less than 2 to the K.
Yeah.
And 1 is of course less than 2 to the K.
Yeah, correct. So the idea is that yeah, I wrote this kind of thing because approximating by rank 1 operators, if AK are just rank 1, all of them are rank 1. I think it will be the problem over here
Yeah.
because these behaves like that's what we need. So we need kind of a dyadic dilations. So it will be a problem with this, but here we can just take the rank 1 operators.
And so here U and V are also normal sequence in H, right?
Yeah. So
And
it's,
do you need to take the 转值咋说的 transform of UK when you consider the tensor?
yeah.
Because that doesn't make sense if you.
Yeah. Okay. Yeah. And without that didn't make sense. That's exactly right. Sorry that. So from now on, we will always assume that the straight E, the shift monotone sequence ideal, and the curvy E, the symmetric operator ideal, they are associated. So the first theorem will be that the operator A belongs to the symmetric operator ideal if and only if. If and only if there exists an dyadic E representation. Of A. Let's do this proof. So first of all, there is an alternative definition of the singular values. So they can be computed in this way for any bounded operator. Mu n A can be computed as the infimum of A minus F with F K such that the infimum over no, just F. We take the infimum over all bounded operator F's such that the rank of F is less than or equal to n. So this is the alternative definition of the singular values, and this is the reason why this, for instance, also is called the nth approximation number. Just another terminology, so another nickname. Okay, yeah. Using this alternative definition, we can claim that for every bounded operator A, there exists operator Fn, bounded operator Fn, such that the rank of Fn is less than or equal to 2 to the power of n, such that A minus Fn is less than or equal to 2 times mu at the point 2 to the power of n. So in fact, mu at the point 2 to the power of n is infimum of this expression over all f with satisfying this condition. Well, so it's quite close to, so we also can find Fn, which is quite close to mu. If we multiply mu by 2, we will definitely get this. Now this A0 should be A1 should be 0. The fancy 0 is a 0. And then we take AK plus 2 equals 2. Fk plus 1 minus Fk for every k equals to 0, 1, 2. Well, it is easy to see that the sum of Ak from 0 to n, I want it to be Fn, so I need to sum to n plus 1. So they cancel each other out. And therefore, A minus these is less than or equal to 2 mu at the point 2n. Then we're proving that A is in E, so we study from, so far we just had the observation for every bounded operator. Now let's go with the first part of the proof. If A is in curve E, then this sequence belongs to the straight E by correspondence. Belongs to the straight E. But straight E is the shift, or rather the monotone sequence idea. And having this inequality, we conclude that this sequence is also E. Almost done. To show that this AK form a E representation, we need to prove this not with n plus 1, but with n minus 1. But fortunately, E is S plus invariant. Well, the half, the first part. Okay, let's now prove the converse of this thing. So we start with E representation, B a dyadic E representation. Well, from this we instantly get that the rank of AK is less than or equal to 2 to the power of k, just by definition. Hence, the rank of the sum is at most 2 to the power of n. Then mu of A at the point 2 to the power of n is less than or equal to this mu. Because this is rank has rank which is less than 2 to the power of n, and this is infimum over all such sums. Again, since this is the E representation, this sequence belongs to E by definition. Belongs to E. Therefore, mu of 2n A also belongs to E, since E is the monotone sequence idea. And And this is by the Pietsch correspondence, means that A belongs to Q. Then fairly simple proof, I would say. And now we will have even simpler lemma. Right. So now we consider two different representations. Let A and B has E representation. We define the dyadic representation for the sum. Then A plus B equals to the sum of say ZK with Z0 to be 0 and K plus 1 to be AK plus BK. K is 0, 1, and so on. Then this is the dyadic E representation for the operator equation. And this is even simpler than the one we proved before, and for this reason we will not even prove it. So I will just explain why is it so. So these two series are convergent in the operator norm. So this one is also convergent in the operator norm, given this condition. We define zk plus 1 to be like this, to make it rank to be less than 2 to the power of k plus 1, because ranks of this one. And again, by the triangle inequality, this type of sequences, they are also in. So that's it. Any questions? Because we want to start, we want to consider the representations such that each operator here, zk, its rank is less than 2 to the power of k. So, and we want to construct it to make this work. We want to construct it from ak and bk, the sum of them. But rank of these is at most 2 to the power of k, and rank of these. So to maintain the ranks, we just set the first one to be 0. Okay, and that was all the preparation we needed for the meaning theorem. Let gamma be S plus invariant operator, functional. Be a linear functional. On the shift monotone sequence ideal. the expression L of A equals to gamma of 1 and 2k trace of AK. So first of all, I use here again the end-user application, so I apply the functional to the sequence, but I'm not putting the curly brackets. AK is, let me just write it here. A equals to AK is E representation. So the third thing we need to prove here is that this functional well-defined, so it does not depend on the particular choice of representation. So this expression does not depend on representation. Representation, that's the first plane. The second plane is that tau is a trace on E. Here it goes to say that A is from E here. Right now. And the third thing is that the correspondence gamma to tau is bijet.
The truth in the bracket is the standard truth.
Yeah, this is the standard trace. Thanks for asking. I wanted to mention that, but I forgot the standard trace.
Pietsch.
Yeah. The usual model. So all these operators are of finite rank, so we can trace them. Proof. Let's go with the first thing. Let's take two distinct E representations and show that the value of tau coincide regardless of this representation. From 0 to infinity of jk. Distinct E representations. Distinct representations. Then set Z0 to be zero operator and Zk plus 1 to be AK plus jk. But this is then a representation of the zero operator by lambda. Is the E representation of second. It's minus. That's what it is. Thank you for the zero operator. So to prove the independence, we need to show that so we need to show that gamma vanishes on the sequence A, which is given as trace of zk over 2 to the power of k. And then we will show that regardless of the representation, we get exactly the same value of the function. This is our sequence A. Yeah, I was writing trace and trace in a different way. Let's go with the one notation. This one. Trace of zk over 2 to the k. 0 to. So the first observation is that A0 is 0, because Z0 is 0. Therefore, if we take A and apply first S minus and then S plus, then we will get A itself. Because the first coordinate is 0, we remove it and then add 0. Okay, let's also define the sequence B, which will be the sum trace Z I from 0 to k.
第一个是零，
因为第一个是零的情况下，它就等于没有。
So that will be our auxiliary sequence. Let's check what we have. If I take now BK minus B half, BK minus 1, then what I have is from 0 to k, to the power of k minus again over 2 to the power of k, because I have divided by 2. So this is nothing but AK. Nothing but AK. And we want to show that every S plus invariant, S plus over 2 invariant functional vanish on A. So we are almost there. We wrote A as a sequence minus S plus over 2 of the same sequence. The only thing we need to show now is that B is in the shift monotone ideal. Because we have written A, so A now belongs to the range of identity minus S plus over 2. But we need to know that this sequence is in the ideal as well. Therefore, A equals to B minus half S plus of B. And now we need to show that both A and B are in there. So let's start with the evident estimate. Trace of an operator, let's go with A, is less than or equal to n times the norm of A if the range of A is less than or equal to. So this is the sum of singular values. The rank is n, so there are only n of them which are non-zero. We take n and here there is the largest of them. Since we're having this, we have AK is less than or equal to the norm of ZK. Because that ZK is of rank at most 2 to the power of K,
Yeah.
and we just cancel it. And now I can write these as zero operator minus J from 1 to K, Z, J, yeah, it's greater than or equal to, or less than or equal to 0 minus J from 1 to K minus 1, ZJ.
Yes.
But since Z is that ZJs are the E representations of the zero operator, we conclude that
This is
so this sequence belongs to E. So therefore, A belongs to E. Good. Let's now do the similar stuff for B. For B, I think we do exactly the same now. Yep. So for BK, we have less than or equal to. So I also estimate. Yeah, I will write it like this. Two to the power of K trace of Z and trace of the sum from 0 to K ZI. The rank of each Zi is at most 2 to the power of I. So the rank of this sum is at most 2 to the power of K plus 1. So it is less than or equal to 2 times the norm of this sum. But Z is again still the E representation of the zero operator. So I can write it as and again conclude that B is E. Okay. So let's go with the computations. So we have gamma of the first representations, A, K, minus gamma of the second representation, equals to gamma of A equals to hold on a second. Yeah, that's a mistake here. So I wanted to rush up and made a mistake. It doesn't change the story much, but is it the trace of ZK or not? is a trace of zk plus 1. By definition. So the only difference is that we have 2 times gamma A. So I divide by 2 now, which is 2 times gamma B minus half S plus of B, since gamma is done with the first part of the theorem. We in fact proved that this formula, that functional, it does not depend on the representation, so we can take any representation, just your favorite one. Okay, let's go for the second part. The second part is trivial. Tau is a trace, since the standard trace is a trace. Because tau is defined in terms of the standard trace. The last third part, we need to prove that the correspondence between gamma and tau is bijective. So we will do it in 2 steps. So first of all, we prove the converse correspondence and then prove the bijective. Take the trace on E, and set gamma to be, or gamma of x to be tau of dx for every x from L of from E. So we know that by the correspondence between these 2 ideals, we know that if x is in straight E, then dx in the curvy E, so this formula does make sense. Clearly, gamma is a linear functional on straight E, because tau is linear and d is bounded operator, well, linear bounded operator. Yeah. We need to prove S plus over 2 invariance. So consider gamma of half S plus of x, which is half tau of d S plus of x. Let's have a closer look on d of S plus of x. By the definition of the operator d, we have that dx is the diagonal operator of this sequence xn, then characteristic function 2n minus 1, 2n plus 1 minus 2, and from 0 to 4. So I just wrote that sequence of repeated x's in a compact form. Then d of S plus of x is diagonal of x n minus 1. We're starting from 1 to infinity now, because the first one is 0, and the same intervals. Let me split these intervals into 2 parts. It equals 2. scale of n from 1 to infinity, x n minus 1, characteristic function of 2n minus 1 up to 3 on 2 to the power of n minus 2 plus the characteristic function of 3 over 2 to n minus 1 and up to the end. So I split this interval right in the middle. The length of this interval is 2 to the power of n. So I will get to the middle if I add 2 to the power of n, n minus 1. That's what I've done. 2 to the power of n plus 2 to the power of n minus 1 is 3 over 2 to the power. So I split it exactly in the middle. Now let's consider sequences. That's a big one. Consider the sequence y to be the first part from there. That's big word for a short time. And the sequence z to be the second part from the And these sequences are just the rearrangements of each other. Because the lengths of these intervals are exactly the same. And on all these intervals, the sequence, either y or z, equals to x to the power of x n minus 1. So the decreasing rearrangement of y equals to the decreasing rearrangement of z. So they are just the permutations of each other. If we consider the diagonal operator constructed with respect to y and take its singular values, then it will be exactly the same as the singular values of diagonal operator constructed by z. But since we have these, the trace of y equals to the trace of of z. So going back there, we have that gamma of half of s plus of x equals to tau of say of y or z, they are the same. On the other hand, the sequence y and the sequence x n minus 1 from 1 to infinity, characteristic functions of function of 2n minus 1 to n. So again, the length of this interval is 2 to the power of n minus 1. And it's exactly the same length as in the definition of the sequence y. And also over this block, this sequence equals to x n minus 1. So these two sequences are again the permutations of each other. But this is quite close to d of x. The only Not the only, it's exactly d of x.
Yes.
It's exactly d of x. We're summing from n equals to 1. In the definition of d, we're summing from n equals to 0. Yeah. Well, diagram of this second sequence. Is nothing but dx.
Yes.
Therefore, gamma of s plus x equals to tau of dx, which is gamma of x. And we are done with the one more part in the equation. So what we have shown is that, first of all, every s plus over 2 invariant functional generates the trace, and every trace generates the s plus over 2 invariant function. So the tiny bit left is to show that it's one-to-one correspondence. The last part, logic. So let gamma corresponds to tau, or rather tau corresponds to gamma. That is tau of A equals to gamma 1, 2k trace AK. And let gamma 1 corresponds to tau. That is gamma 1 of x, here A from the curly E, equals to tau dx, and here x is from E. Well, first of all, to combine these, we need to write down any E representation of the operator D. And that's fairly simple. Take dk to be dialog of xk, 2k minus 1, 2k plus 1 minus 2. Just the diagonal operator of the building blocks for the operator D. Then D equals to dk is dyadic E representation. Therefore, gamma 1 of x equals to tau of dx. So we substitute dk's over here. So it's gamma on this trace of d case. That's actually, yeah. Let's go with it as dkx, because this operator d of x is an operator in the idea. By computing trace of these operators is just the sum of what we have over here. So it's ak repeated 2 to the power of k times. So we get gamma of 2 to the power of k x, which is gamma of xk. Let me go with the fancy one, or gamma of x. And so we have proved that the correspondence is quite objective. You also can compare the previous proofs of constructions of singular traces to this one. First of all, this one did not require any previous knowledge of anything. Well, maybe the gradient course in functional analysis. So we didn't use any subtle inequalities on singular values, for instance, which we needed before that, and we needed it both-sided. So the only thing, so this is kind of material or kind of proof which can be presented like to year 4 university students, because like we didn't use anything but the classical functional analysis in the proof. And in the words of Albert Pietsch himself, this approach reduced the construction of traces from the mountain climbing to the walk in the garden.